Here's a puzzle. The Fibonacci sequence starts 0, 1, 1, 2, 3, 5, 8, 13, 21, and each term is the sum of the 2 before it. So what is the 100th Fibonacci number? It's roughly 3.54 times 10 to the 20th. And its growth rate turns out to be the golden ratio, about 1.618. Why does that number appear? The answer is eigenvalues. To answer that, we need a general machine for dynamic systems. A difference equation has the form u sub k plus 1 equals a times u sub k. Each step multiplies by the same matrix A, starting from u sub 0. After k steps, we get u sub k equals a to the k times u sub 0. That formula looks clean, but computing a to the 100th power directly is brutal. The matrix multiplications pile up and the entries explode in size. So we need a smarter route. The trick is to break u sub 0 into pieces that A handles trivially. Those special pieces are called eigenvectors. Recall that an eigenvector x satisfies A times x equals lambda times x. In other words, multiplying by A just scales the eigenvector by the number lambda, right? And that's the key property we'll exploit. So let's expand our starting vector u sub 0 in the eigenvector basis. U sub 0 equals c1 times x1 plus c2 times x2, and so on up to cn times xn. Now apply a to both sides, because ax1 equals lambda 1x1 and ax2 equals lambda 2x2. Each eigenvector just picks up its own lambda. So a times u sub 0 equals c1 lambda 1x1 plus c2 lambda 2 x2, and so on. Apply a again, and each term picks up another factor of its lambda. After k steps in total, each eigenvector has picked up lambda to the k. So the solution is u sub k equals c1 times lambda 1 to the k times x1 plus c2 times lambda 2 to the k times x2, and so on. In compact matrix form, u sub k equals s times capital lambda to the k times c, where s holds the eigenvectors in its columns, capital lambda is the diagonal matrix of eigenvalues, and c is the vector of coefficients. The beautiful thing is that each eigenvector evolves independently, no coupling. Right? As a quick example, with lambda 1 equal to 2 and the lambda 2 equal to 1/2, watch what happens as k grows. The 2 to the k column goes 1, 2, 4, 8, it blows up, while the 1/2 to the k column goes 1, 1/2, 1/4, 1/8, it shrinks to 0. Let's watch this machine eat Fibonacci. The recurrence f sub k plus 2 equals f sub k plus 1 plus f sub k is second order. It looks back 2 steps. We convert it to first order by stacking 2 equations. Define the state vector u sub k as f sub k plus 1 on top and f sub k on the bottom, then f sub k plus 2 equals f sub k plus 1 plus f sub k, and trivially f sub k plus 1 equals f sub k plus 1. Written in matrix form, u sub k plus 1 equals the matrix with rows 1, 1, and 1, 0 times u sub k. We'll call that matrix A. Notice that A is symmetric, so its eigenvalues will be real. To find them, we solve the determinant of A minus lambda times the identity equals 0. The matrix is 1 minus lambda in the top left, 1 in the top right, 1 in the bottom left, and negative lambda in the bottom right. Its determinant is 1 minus lambda times negative lambda minus the product of the off-diagonal ones. Expanding gives negative lambda plus lambda squared minus 1, which simplifies to lambda squared minus lambda minus 1. Setting that equal to 0 gives the characteristic equation lambda squared minus lambda minus 1 equals 0. Now pause on this. The characteristic equation is literally the Fibonacci recurrence in disguise. If you rearrange f sub k plus 2 minus f sub k plus 1 minus f sub k equals 0, you get exactly the same shape. That is not an accident. We built A to encode the recurrence, so its characteristic polynomial re-exposes it. Now apply the quadratic formula to lambda squared minus lambda minus 1 equals 0. Lambda equals 1 plus or minus the square root of 1 plus 4, all divided by 2. That simplifies to lambda equals 1 plus or minus the square root of 5 all over 2. So our two eigenvalues are lambda 1 equals 1 plus root 5 over 2, which is approximately 1.618. That's the famous golden ratio. And lambda 2 equals 1 minus root 5 over 2, approximately negative 0.618. Let's do a quick sanity check. The sum of the eigenvalues should equal the trace of A. Adding them gives 1, and the trace 1 plus 0 is also 1. Good. The product of the eigenvalues should equal the determinant of A. Multiplying gives 1 minus 5 over 4, which equals negative 1. And the determinant of A is also negative 1. Both checks pass. Remarkably, the golden ratio has emerged from a simple 2 by 2 matrix made of 1s and a 0. Now let's find the eigenvectors. Here's a clever guess. Try a vector of the form lambda 1. Let's check what happens when we multiply A by this vector. A is the matrix with rows 1, 1, and 1, 0. Multiplying A times the vector lambda 1, the top entry becomes lambda plus 1, and the bottom entry becomes lambda. We need this to equal lambda times the vector, which is lambda squared on top and lambda on the bottom. The bottom entries match automatically. That's a freebie. For the top entries to match, we need lambda plus 1 equals lambda squared. But that's exactly our characteristic equation, just rearranged. So the guess works for both eigenvalues. And therefore, x1 is the vector lambda 1, 1, and x2 is the vector lambda 2, 1. Both eigenvectors drop right out of the very same equation that gave us the eigenvalues. Now we apply the general formula for powers of the matrix. Start with the initial vector u sub 0, which equals f1 on top and f0 on the bottom. That is 1, 0. Next, expand this vector in the eigenvector basis. 1, 0 equals c, 1 times the vector lambda, 1, 1 plus c 2 times the vector lambda, 2, 1. Matching the bottom entries gives c1 plus c2 equals 0, and matching the top entries gives c1 lambda, 1 plus c2, lambda 2 equals 1. Solving these, we find c1 equals 1 over the square root of 5, and c2 equals negative 1 over the square root of 5. Therefore, u sub k equals 1 over root 5 times lambda 1 to the k times the eigenvector lambda 1, 1 minus 1 over root 5 times lambda 2 to the k times the eigenvector lambda 2, 1. Now read off just the bottom entry of this vector. F sub k equals lambda 1 to the k minus lambda 2 to the k, all divided by the square root of 5. That is Binet's formula, like a beautiful closed form for every Fibonacci number. Here's where dominance shines. Lambda 1 is about 1.618, bigger than 1 in absolute value, so its powers explode. Lambda 2 is about negative 0.618. Its absolute value is less than 1, so its powers die off. In fact, lambda 2 raised to the 100th power is on the order of 10 to the negative 21st, utterly negligible compared to lambda 1 to the 100th. So f sub 100 is essentially lambda 1 to the 100th, divided by the square root of 5, the golden ratio raised to the 100th power, rescaled. That gives roughly 3.54 times 10 to the 20th. One eigenvalue, one calculation, and you skip 99 additions of the recurrence. The lesson generalizes. In any linear dynamical system, the eigenvalue with the largest absolute value dictates long-term behavior. Components tied to eigenvalues with absolute value less than 1 vanish. The dominant mode wins. Step back and see the bigger picture. Linear algebra really has two personalities. The static problem asks ax equals b. Solve once, find x, done. Eigenvalues are irrelevant here. The dynamic problem asks u sub k plus 1 equals a times u sub k. The system evolves in time. And here, eigenvalues are everything. Right? They tell you about stability. If every absolute lambda is less than 1, the system decays to 0. They tell you about growth. The largest absolute lambda sets the rate. Right? They tell you about oscillation. Negative or complex eigenvalues produce sign flips or rotations. Fibonacci is just one example. Population models, Markov chains, compound interest, and the digital filters all live in this same world. And here's a preview. In continuous time, the equation becomes du dt equals a times u, and eigenvalues move into the exponents. Solutions look like e to the lambda t times an eigenvector. Same machine, same insight. Eigenvalues are the dynamics. The golden ratio was hiding in plain sight, just waiting for a 2 by 2 matrix to reveal it.